Next, you'll hear from two leaders who are at the center of the fierce battle over AI hardware. You'll also hear how investment, supply constraints, and national interests are shaping what comes next in semiconductors. From cutting-edge chip design to those bigger geopolitical questions, they'll help us break down the high-stakes competition in AI chips. Please welcome ARM Executive Vice President and Chief Commercial Officer Will Abbey, Graphcore founder, CEO, and Chairman Nigel Toon. They'll be in conversation with yours truly. Please welcome them. Hello, gentlemen.
Hey.
Thanks for being here.
Thank you for the invitation.
Oh, we're going to talk about this whole chips thing.
What's that?
What's that? I think you call it fries in the UK, right?
That's right.
But I digress. Okay, the semiconductor industry, let's level set. 19% global growth last year, 2024. This year, even better. That is about 700 billion globally, I believe. Incredible, fast-moving train of growth. What could stop that? Will, Nigel, either?
I mean, when we look at AI,
Yeah.
which is very, very topical, this event's all about AI, it is insatiable in the performance that's required to run these new workloads, to create models in the data center, to run applications at the edge. It's all about performance. What's going to get in the way of performance? You need power to enable performance at scale to take place. And so for ARM and for the industry, power and not getting enough is going to be a fundamental problem. There are ways in which you can solve it, right, with a power-efficient architecture.
Yeah.
And we think the industry is embracing this idea that power is a scarce resource. So even though I recognize the simple fact that power is going to get in the way, there are solutions around that, and I'm sure we're going to get into.
That's right, and we have some folks in this room who are from the energy, the oil and gas industry, so the burden is on you, folks. All right, Nigel, you agree?
I completely agree. You know, power, if you look at the way data centers were built just a few years ago,
Yeah.
maybe 20 kilowatts in a rack. Now racks are 400 kilowatts, going to a gigawatt.
Yeah.
In a rack.
Yeah.
We're going from air-cooled to liquid-cooled. We're completely changing the way that data centers get built. That density of power and cooling is just, it's mind-blowing, the amount of power that needs to be delivered to these sites. And so if you look somewhere like China, where they have really good power distribution, you can build a data center and you can get power to it. You look in North America, and companies are coming up with all kinds of strange solutions. They're using generators to produce the power that's needed for some of these data centers. So power is a huge limiting factor here as well. And then I think, you know, also just the talent that's needed to kind of keep it all going as well is another area where, you know, there's just an insatiable demand now for chip engineers, which is just a huge change. We've had this lull where not enough people have been going through university studying microelectronics, and there's a lack of young graduates coming through with the necessary skills. So you're having to look everywhere in the world to build the teams necessary to achieve this.
Absolutely. I want to come back to talent, but I want to focus on the power thing for a minute. As a famous rapper once said, racks on racks, stacks on stacks, right? So, like that?
I like
So this is a tremendous change, right? We were pushing chips that were brawny and powerful and performant, and now we're thinking about efficiency because we're looking at the curve and going, this is not sustainable, right? Obviously, we need infrastructure changes, and we could spend a whole talk just talking about the municipal public-private partnerships that we need to put that infrastructure in place. But we're here to talk about chips. When did this shift change, and how are we building and distributing chips differently as a result? Because you can't build a chip overnight. It's a process.
Yeah, I mean, there's a couple of factors. You know, firstly, just when we need more power-efficient chips, Moore's law has come to an end, or scaling. This idea that every 18 months, transistor count doubles, and so for a given power threshold, you can drive more performance. So the industry over the last 40, 50 years has relied on this idea that chips are going to get faster, right, and power is going to be maintained. That's no longer what we're dealing with.
Right.
And so it begs the question: how do I think about power, recognizing that power is a scarce resource? For ARM, this idea is not something that we've stumbled upon. Fundamental to the mobile revolution, if you just think about the fact that a mobile processor has an applications processor, it's got a modem, it's got an image capability, it's got digital power, it's got all of these things on a complex SoC. And so designing with this principle of power efficiency is something that we believe is fundamental to enabling performance whilst keeping power efficiency to a minimum. You can't keep throwing more and more data center racks at the problem. You need to think differently about first principles. If power is a scarce resource, how do I deliver performance without tripling my power budget?
Yeah.
And so that's the way in which we think the industry is going to survive and grow.
Right. Nigel, how's that changing the design process of these chips? Like, for those of us who don't know how a chip is made, this push for efficiency, what is that doing to the business?
It's very hard because, as Will says, the fundamentals are not working in our favor anymore.
That's right.
So you are pushing on the limits. And so you can look at NVIDIA as an example here, and the huge improvements in performance have come with a huge increase in power consumption, because you just don't have this ability to scale and reduce the power that we used to. We're past that limit now in semiconductor technology.
It's a business risk, right? I mean, it's costly, and it's not exactly a great reputational moment when people can't get enough power to their house or their home because of these huge data centers, right?
Yeah, no, it's true, but still the amount of power in absolute terms is still quite small. In the order of 2 to 3% of the world's electricity is data centers, and maybe that's going to double. So maybe it gets to 6% of the world's electricity, which is a big amount. It's like the same amount of energy as the aviation industry uses. So we're talking about a big impact here, but it's electricity. One of the things I look at and say, okay, well, AI is probably our best chance to actually find ways of turning this electricity into green energy, whether that's carbon neutral or carbon zero. AI is the way we're going to solve that problem. So actually the solution to the problem may actually be in converting the energy sources to something which is sustainable, and then you've got more and more energy, more and more performance to create even better AI.
Yeah, and we're focusing on the compute part of the problem, but you've got to look at the full stack, right? You've got to look at memory access, you've got to look at packaging, how do I cool that device? And so it's not just the CPU, which obviously is important from an ARM perspective, but it's a total solution, right? I think you've got to look at first principles. How do I solve the problem holistically? And it can't just be left to one sort of innovation. Across the sphere, ecosystems need to come together, partnerships need to come together, and look at the
well, I think the key is the processor is no longer one chip.
Yes.
Yeah.
It's no longer one die.
Right.
Yes.
The chip is multiple die inside a package. The computer is multiple packages inside a rack, all connected together, working as one computer.
Right.
So you're talking about hundreds of separate processors. I don't mean cores. Within that processor, there's another core. There's hundreds of cores. So we're talking about massively connected systems. So memory access, networking. These are all areas of dramatic change. The networking one I think is really interesting because we're kind of at the limit of what we can do with copper. Every time you double the data rate over copper, you halve the distance at which you can send that information. And so we're now at the point where copper is running out of road, and there's a big shift towards optics. So silicon photonics is suddenly a huge boom area because that's the way we're going to solve how we connect all of these chips together.
The fun thing, right? You're pushing up against the boundaries of physics. Gotta love chips.
Feels like we're in a Star Trek movie or something.
That's right. Well, when you say you're pushing the limits of copper, you're really not everybody operates like semi.
I know we're just in the interest of time, but the industry also needs to think about this idea of custom silicon.
That's right.
And so you got to look at the workload that you're trying to run and where you're trying to run that workload. And the idea of just relying on a general purpose architecture may have worked in the past, but right now that's not the way the industry is thinking. And so from the hyperscalers, whether it's Microsoft, Google, AWS, they're all thinking about custom solutions, right? Custom silicon based on an ARM CPU, right? Tightly coupled with an accelerator, because again, it needs to be power efficient.
Right. Can we dwell on that one? I have one question on that, and then I promise I want to change gears a little bit. I'm glad you talked about custom silicon. How is the demand from the hyperscalers, like you articulated, changing your business? The demand is extraordinary. They want the most cutting edge of chips. They want them, of course, naturally at scale. How's it changing the business for you?
I think it's really interesting. The challenge you have is AI is not fixed.
Yes.
AI is moving at an incredible rate. And so what works today won't necessarily work next year.
Right.
You know, you just look at the shift that we've gone through from the sort of image-focused first generation of AI using convolutional neural networks to transformer-based large language models. Now we're into agentic AI. You know, what's coming next? Diffusion language models, new ways of thinking about the way these models get built, mixture of expert models. And so the compute demands and the type of compute is changing dramatically. The demands on access to very, very large, very high bandwidth memory is enormous, the way in which we connect these chips together. And so it's really difficult you've got to be ahead of the curve, understanding how the workloads are evolving, because software you can produce tomorrow.
That's right.
Chips take months, if not years, to
That's
develop.
right.
And so you've got to be way ahead of the curve in terms of understanding what comes next and building the architectures. You know, the famous Wayne Gretzky quote, skate to where the puck is going, not where it is today, right?
Of course.
Yeah, we just also need to be mindful that AI is not just about data centers.
Yes.
Right? There is this drive and push towards edge applications. And so, you know, my car is an edge application, but more importantly, you know, the devices that we hold in our hand, the models are now running not just in a data center, but models are now running on devices. And so this interplay between what's taking place in the cloud, what's taking place on endpoints are real. And so architectures that stem themselves from cloud to the edge.
Yeah.
You know, for ARM, we play in the data center, we play in the edge, and the two worlds can come together.
Is that where the puck is going, by the way, that we're pushing the AI to the edge and we're going to see less emphasis on the data center and more on the smartphones in our pocket, the smart cars in our driveways?
I think you're going to see innovation taking place at
in
both ends, right?
Okay.
So new models, new ways of thinking, as well as workloads that are running on end devices. I can't think of a given application today. You look at Siri's running not just on your device, right?
That's right.
It's running in the cloud.
In the cloud as well.
Right? And but where we need sort of higher bandwidth, we need latency, you need an answer instantaneously, that's going to run on the edge. Where it can, it's going to push that information back to the cloud. So this instant sort of interplay between the two forces are going to continue to prevail.
You're seeing a really interesting trend where actually I think we've seen peak model.
Peak model. We've reached peak model. Is that what you're saying?
Because what's happening now is rather than everything going into one model, all the information being pushed into one model, all the parameters in one model, we're moving towards mixture of experts. So many more smaller models all cooperating and working together. And so what that really means is at the edge, you can have some of those models actually operating locally, low latency, high performance, connected to models in the cloud that are providing that broader level.
Different chips for them.
And you need different chips for both. And then the key is the access to information that you need associated with those. Because this is a piece which is kind of the sort of hidden piece of AI is all driven by the information that it has access. And I distinguish between information and data.
Yes.
Because information is data with context.
That's right.
And so you think about, when you use an AI system, how much information about yourself are you willing to share with it? Because that context is going to allow you to have much, much better answers from the AI system. But it does mean you're going to share a lot of information with the AI system to get those better answers.
Right. So let's change gears, because I promise we have the word war in the title of this session, and I would be remiss if I didn't focus on the kind of global, war, right? Battle, fight, competition over chips. What's going right and what's going wrong as all of the world's great powers vie to be the best at chips?
Well, firstly, I mean, it's all love and peace on the stage here.
It's all love and peace. No chips war here. You heard it first.
There's no taking place. But look, I mean, ultimately, I think countries, sovereign states, recognize the fact that information and data is key.
Yes.
Right, and you need to maintain and control your own data and infrastructure. Right, and so that and the fact that there's tension between countries and states indicates that that AI is precious and important. Right, and so what's going right? I think the maturity of the industry, the prize of AI, is forcing everybody to think differently around controlling data, building out your own infrastructure, which I think is a good thing. Semiconductors and AI's moved from the background, right, to center stage, because of the fact that controlling data, controlling infrastructure, and also looking at economic benefit of building out your own economy around semiconductors, around tech, is a good thing.
Well, that's why I ask. On the one hand, you're getting tremendous investment from each one of those nations or municipalities or whatever level you want to talk about.
But it's also a fracturing.
On the other hand, you're getting restrictions, right? Competitive hurdles for global enterprises that would care not to have those.
What we built through the 90s and 2000s, semiconductor went from being a highly verticalized industry into being a very outsourced industry, with specialists emerging at each of the layers, the emergence of TSMC, the foundry level, ASML, at the manufacturing machine level.
You're talking about the decline of the Intel model is really...
And this sort of, so we built this highly efficient, layered infrastructure with distribution all around the planet. And what we're now going to is people going, oh, hang on a second, that's a bit dangerous. How do we gain back control over this? And can we build, again, verticalized structures in Europe or in North America? And what people miss, I think, is the cultural aspects to this. Why are the most advanced semiconductors built in Korea, in Taiwan, Japan? Because these environments are places where that very, very high quality manufacture is truly valued. There's an ethos around it that actually doesn't exist culturally in some of these other countries. So trying to import that culture, one of the biggest challenges they're having in building these new fabs in North America is actually getting people to work in those that just deal with the idea, I'm going to make this better every single day. And so there's a big, this is not like build a factory, plug it in and off you go. This is so intense in terms of the daily improvement, the weekly improvement, the monthly improvement that is driven through these systems, and it's fundamentally cultural and very, very difficult to see how you transplant that. And so my personal view is this current focus on trying to build verticalized systems across the world, I don't think it's going to work. I think we're going to have to find a way, an accommodation where people can say, I own this critical piece. Europe owns ASML, and that's a critical piece. America owns the design capability, that's a critical piece.
It's forever a
Taiwan owns the manufacturing piece, that's a critical, and we've somehow got to find a way of accommodating and working together around this. But in the current environment, that's really, really difficult to see how we reach that accommodation.
And I'm in agreement with Nigel that in an ideal world, it'll be love and peace, everybody will work together.
Flower power, sure.
But the reality is that that's not the reality of what we're dealing with. And so whether it's France, whether it's Malaysia, whether it's Singapore, I think you need to think about controlling your own destiny. You need to think about recognizing that the infrastructure that's relevant to you, something that you can own and control and build, and companies like Arm are willing to work with you to equip you, to enable you to control your own destiny.
So with all this landscape that you've just outlined, as we kind of come to our conclusion here, do do we think in the year ahead, given all of the constraints that we were talking about globally, things are going to get better, meaning easier, or worse, harder for the semiconductor industry? Will?
Yeah, I'm an eternal optimist, and so I think that things will get better. I think the AI cycle that we're in, this super cycle that we're in, I think it's real. I think we're still at the infancy of that. And I do believe in this collaboration mindset that the industry has had. And so I think that's going to enable us to solve these problems at scale. I also think that we need to have a malleable mindset because of the pace of which AI is sort of transforming. Models are transforming. What worked yesterday is going to be fundamentally different in terms of what's going to work tomorrow. But I am an optimist, and I do think that we're going to all benefit from this AI super
Do you
scale.
share his optimism?
I think the big challenge here is you think it's fast today, it's going to get way faster. Because imagine a situation where AI, today it's helping us code. Soon it will be helping us make new AI models. And the AI models will get better and better, faster and faster. This is only going to speed up. It's going to create more needs for compute. It's going to create more needs for power. All of the things that we have been talking about, this stuff is just going to speed up. And we're heading into a fast-forward future.
There you go. So strap in. Gentlemen, this was a wonderfully insightful conversation. Thank you so much. A round of applause.
Thank you.
After you.